Good morning, everybody. Um,
Good morning.
please go ahead and mute yourself and go ahead and type in the chat box for your attendance for today. And we'll get started in about 3 minutes or so. Okay. So good morning, everybody. We are going to get started on our second lecture for the semester, which is going to be the chemical level of organization. So last time when we discussed introduction to anatomy and physiology, our focus was more on, okay, so what is anatomy? What are our body system? Um, what are the typical ways for us to distinguish structures based on their locations? We actually went ahead and did a lab on that as well, which was a lab you guys did for the first week of the semester. Now, what we're going to move on to is looking at the organizational levels that we discussed also during the first week, which was starting with chemical level and then building on the chemical level, which is the most basic level, going to the second level, which is cell. And from cell, we went to tissue, from tissue to organs, and organ to organ system. And then finally, all of the organ system came together to basically form your organism, which is in this case would be us as a human being. So this is one of your Canvas posts. I don't know how many people have already answered that, but that's one of the Canvas posts that you guys were asked to do. And then also in terms of providing an example for it. So what we're going to do today, we're going to actually talk about the first two levels of organization, which are chemical level and organizational level, chemical levels and cellular level. The information I'm covering here are relatively basic. It's just to kind of get you guys get started in terms of understanding what that level of organization looks like. But as I mentioned last time in our intro, our focus is going to be on organ system, which is basically doing a systemic review of the organ system, the 11 organ system we have, to figure out how each of them basically, or what are the organs within each system and what is the generic function of each of those organs. So hopefully you guys get the joke that I have here. It says oxygen and magnesium together, OMG. If that doesn't make sense, go find things on periodic table and hopefully that makes sense. I don't know, I have a lame sense of humor, I guess. Anyways, so moving on, so let's go ahead and get started. So when we're talking about chemical level, which is basically the most basic level of organization we have, it's actually made up of two things, atoms and molecules. And I asked you guys this question last time, and I said, if I want to get information about atoms, where can I get it? And some of you were able to answer the question that the place would be periodic table, which is a correct answer. So if you ever taken chemistry, you've seen that gigantic table, which is basically a bunch of letters, and then it has numbers on top and bottom. Again, our goal is not to learn about periodic table or to memorize every single element that we have. Our goal is to understand its relationship to the anatomy of our body. So that being said, you do need to know some of the atoms that are found inside our body and the shorthand of it that you can find on periodic table. For instance, as I provided for you guys, the letter C or capital C represent carbon, which is basically the most important building blocks of us as human beings, or any living organism on planet of Earth, if I should say. So the first question is, so what are atoms basically? So atoms are basically the smallest component that has the characteristic of a specific element. So that characteristics are basically both chemical and physical property of an element. So let me give you an example. So when you look at the periodic table, gold, I always give the example gold because everybody's like, oh, gold. So the periodic name, or I guess the cellular symbol, I can say, the symbol for gold is AU, capital A, lowercase u. So if I take that and I say gold is an element in my periodic table, and I said, I'm going to have a chunk of gold and take the smallest piece of the smallest piece of the smallest piece of that gold. And that piece of gold, even though it's super small, it still has the same characteristic as that chunk of gold. What are those characteristics? Are both chemical and physical characteristics. So that the smallest piece that I separated that can represent an atom of gold, and then the chunk of gold that I have is the element of gold. Technically, they are not different. So when I'm talking about atoms, for our purpose, if you're taking a biology, when you use the word element and atom, they represent the same thing. Atom is just going to be the smallest of the smallest of the smallest piece of that element. Now, when you look at an atom, you have what we call subatomic particles. So subatomic, anything you think about sub, it means it's below something, right? Like subway. So subatomic particles basically describe the components an atom is made up of, okay? So these are proton, neutrons, and electrons. So you probably have heard of this again if you haven't taken any type of biology or chemistry class. If you look at the environment around you, you have charges in your environment, right? Even if you look at the battery that we have. Those charges, the two common ones are positive and negative, right? The two ends of your battery. However, we also have the third option, which is basically an option of neither positive nor negative. And that's referred to as the neutral charge or charge of zero. So when we're looking at the atoms and the subatomic particles of that atom, we have those three charges associated with these three subatomic particles. So, for example, P for proton, right? The charge that proton carries is a positive charge. So I always tell my students, easy to remember, P for P, right? Positive charge are associated with subatomic particles called protons. The ones that are neutral, which means there is no charge with them, are referred to as the neutrons. And the only charge that we're left with is electrons, which are going to be negatively charged. So when we look at an atom and we say, okay, where can I find the proton? Where can I find the neutron? And where can I find the electron? The location of the proton and neutrons, so the positive charge and the one that has zero charge, are found at the center of your atom, a space called nucleus. Electrons, on the other hand, which are your negatively charged components, are orbiting around your atom. So a lot of people used to describe this as our solar system. So the sun, basically, which is at the center, would be where you can find your proton and neutrons, which is your nucleus. And basically the planets that circle around the sun would be your electrons. And again, they have that negative charge associated with them. If there is any questions, again, guys, please type your questions in the chat box. And I have let several people in already, so please make sure you type your name on the chat box for your attendance. Now, the next thing that we have is molecules. So I mentioned earlier that the chemical level is made up of atoms and molecules. So we already talked about atoms. So what is the definition of a molecule? So molecules are basically particles that are composed of two or more atoms held together using a chemical bond. So kind of putting the words in perspective, anytime you hear the word chemical bond, think about that as a glue. Basically something that's going to stick two atoms together, okay? So the word chemical bonds, again, it's the glue that holds the atoms together to form what we call a molecule. Now, when we think about molecules, please be careful. It doesn't have to be different atoms coming together to form your molecule. As far as there's two atoms, even if they are the same atoms and they come together, that would be using to make what we call a molecule. For instance, in this example, I gave you atoms of the same type. In this case, two oxygen atoms have come together, and that gives me the oxygen gas, right? Or O2, two atom molecule, two oxygen, or two atoms of oxygen. And if we're putting two different atoms together, we have hydrogen and oxygen coming together to give me my water. And hopefully everybody knows the equation for water. Can you just type it quickly in your chat box? I want to make sure everybody's know that one. That's an easy one. H2O, correct. What about if I say carbon dioxide? What is carbon dioxide? CO2, correct. So when you're looking at your atoms and molecules, again, it doesn't matter as far as there's two atoms, even if they're the same or different, they come together and they're glued together using chemical bonds, we refer to those as a molecule. Now, going back to what I was mentioning earlier, there are some atoms that I do want you guys to be comfortable with, because it's going to be something that I will be mentioning, both in terms of your, I guess, your lecture for anatomy, as well as your lecture for physiology later on if you take it. So these are the shorthands that I expect you guys to know in terms of the specific atoms we're concerned about when we're talking about our body. And these atoms are, so one is potassium, and I'm typing in the chat box so you guys have that knowledge as well. It's capital K. Yes, you can put the positive on it, but for now, we're not talking about the positive and negative. The other one is sodium. So sodium is capital N, lowercase a. The next one we have is calcium. So calcium is capital C, lowercase a. The other one that you need to know is chloride. So it's hard for me to type and talk at the same time, which is capital C, lowercase l. Is there anyone that I need you guys to know? Oxygen, we already know. Carbon, we know already. So those, I think those are the only ones that I need you guys to know. So again, these are typical exam question, guys. What is the shorthand for calcium? What's the shorthand for sodium? What's the shorthand for oxygen, etc. So make sure you guys feel comfortable with those letters. Okay, any questions so far, guys? Does this make sense? Again, please type your questions. Don't be shy. Time's up. Thank you. Awesome. Okay. So we said that when we look at your molecules are glued together using bonds, right? Chemical bonds. So there is two types of chemical bonds that I do want you guys to know. And this is really, really simplified, guys. So I'm not gonna go into a lot of details for you guys, because again, this is not a chemistry class, but you do need to have a very general understanding of where these signs come from when you say, you know, chloride is negative or sodium is positive or calcium is 2 positive. Kind of, I wanted you to understand where these actual numbers come from. So one type of chemical bonds that we have is called ionic bond. So ionic bonds is when you are dealing with electrons of 2 atoms. So again, let's assume you have 2 atoms, and these 2 atoms are want to come together to form a molecule. One way they can do that is one atom is going to give up its electrons, and the other atom is going to pick up those electrons. So it's a matter of gain and loss of electron. So the bond, that chemical bond, that glue that we keep talking about, is formed because one atom is losing its electrons and the second atom is picking up those electrons. So here when it says Ame1, you can make a note for yourself. In this case, when sodium becomes positive, oh, well, let me back up actually. When we're talking about an atom, and I want to just kind of quickly make a note for you guys. Let's say we're talking about sodium, okay? When we're starting sodium by itself, it's not forming any chemical bonds with anything. The overall charge on sodium is 0. The reason the charge on sodium is 0 is if I compare the number of protons. What is the charge of proton, guys? What's the charge of our protons?
Positive.
Positive. Correct. So if the charge of the sodium is positive, let's say sodium, and these are arbitrary numbers, guys, I'm just making this up. So let's say sodium has 14 positive charges, okay? And I'm going to put a positive on the top. The charge of electron is negative, right? So if I have 14 positive charge in a sodium by itself, it's not forming any bond with anything else, it will have the same number of electrons, which is 14. So if I look at the overall charges, my positive will be canceling my negative. So the overall charge would be 0. If I do the same thing for my chloride, again, starting with 0 charges, and let's say the number of protons and the number of electrons. Let's say protons, these have 10 positive charge, okay? And electrons are gonna be 10 negative, right? Because you need to have the equal numbers so they can cancel each other out. You're gonna end up with 0. So what happens when you are creating, one second. What happens when you're creating an ionic bond to bring the sodium and chloride together? In that scenario, sodium is gonna lose one of its electrons to chloride. So the arrow that I'm showing is that sodium's gonna lose an electron and chloride is gonna gain an electron. So pay attention because this is where my students get confused. So when you lose an electron, your protons are not changing. You still have 14 positive protons. But your electrons, because you're losing one, become only 13, right? Because you're losing one. So now you have 14 positive, take 13 away. What's your overall charge? 1 negative. Oh, sorry, 1 positive. I can't actually. 1 positive, right? 14 positive, 13 take 13 away. So it becomes a positive 1. Chloride, on the other hand, you have gain an electron. So your new number for electron are 11 negative, right? So you have 11 negative. You take 1 positive away from that. You end up with 1 negative. So how do I write that on the sodium? The sodium will be highlighted with a positive 1. And chloride would be just a negative sign. What do we call something that has that positive, the one that has lost an electron? We call those cations, and this is again exam questions. What are the ions that have lost electrons? They're called cations. And the ions or atoms that have gained those electrons and become negative, we refer to those as anions. Again, exam question in terms of what is that positive charge, negative charge, and how are they attained. Positive charge is attained by losing electrons. Negative charge is by gaining that electron with the negative charge. Now, on the same note, when I go back to the ions that we described, the proper way of writing those ions, and I'm typing this again in chat box so you guys can have it, is potassium is K1 or K plus 1, I guess. Chloride, as we mentioned, is negative. Sodium, as we mentioned, is positive. And calcium is another one that we need to know is 2 positive, which means it has lost 2 electrons or lost 2 negative charges. Any questions about this? Give me a thumbs up on your screen so I know that you guys are okay. That way it's easier instead of you guys typing. Awesome. Perfect. So when we're looking at your ionic bond is loss and gain of the electrons, right? Covalent bond, which is another type of bond that we have, is the electron of one atom is not completely lost. Rather, to form the molecule, the glue that brings these atoms together, is sharing of the electron. So not gain or loss of electron, that one is basically losing something versus the other one gaining something. Covalent bond, they said, okay, we are two atoms. Let's be mature about it. Let's put what we have in the middle and let's share them. I know the atoms don't talk, but the idea is there. So when we're talking about covalent bond is basically atoms of the different atoms are going to share their electrons with each other. Now, it's not mentioned here, but I do want to make this clear to you guys. So when we're talking about covalent bond, there are two types of sharing. One share is equal sharing. Sorry, my thing is not really working. So I'm just going to type in the chat box to make it a little bit easier. So if I have equal sharing, okay, it's referred to as the non-polar covalent bond. So if it's equal sharing, it's called non-polar covalent bond. So basically, imagine you have a pizza between two people, one person gets half, the other person gets half. You're really not distributing anything unevenly. So we refer to these as non-polar covalent bond. So by just simply saying covalent bond, that's not sufficient. You need to go a little bit more detail. Non-polar covalent bond. Now, if you have unequal sharing of electrons, then that's referred to as polar covalent bond. Again, guys, these are exam questions, so make sure these make sense to you. So unequal sharing, so let's say again, the example of pizza. One person takes a quarter of the pizza and the other one takes 3/4 of the pizza. That's an uneven sharing, and that type of bond is called the polar covalent bond. The reason it's called polar covalent bond, because you have charges which are either slightly negative or slightly positive. So poles, like the poles on the battery, positive and negative, it's not fully, it's partial charge or a slightly negative or slightly positive. When you have equal sharing, neither of them are going to be positive nor negative, so they're considered non-polar. And literally, that's all I want you guys to know when it comes to the type of bonds we have. Sharing equally, sharing unequally, or complete gain or loss of your electrons. Good? Make sense? Yeah, just thumbs up to me. That's the easiest way for me to figure out. Or you can type yes, that's fine too. Whatever works for you guys. Awesome. So let's move on to the next step. So we're talking about molecules right now. So we learn multiple atoms come together to form a molecule, and that molecule is basically eventually going to be used to form your cells, which is the next organizational level. Now we're going to start here by looking at the molecules, which are the basic part of our life as humans. And these molecules are referred to as organic molecules. So the key word here is organic. And I don't mean that, like you're eating organic food, very limited in pesticides or a modification, gene modification. That's not what we're talking about here. Organic molecules, we're talking about them as the most basic level. And what the word organic implies, that means, highlight this for yourself. Again, typical exam question. That it contains carbon and hydrogen, guys. So when I use the word organic molecule, what I'm talking about is presence of both carbon and hydrogen. So think about the fact that as humans, right, if you burn a body, what's the most common thing that is left over is ashes, right? Ashes are basically what? Carbon. Hydrogen is always come with carbon because it's essential to make molecules that are make it basically give us the ability to live. So I tell my students to think about this when we're talking about organic molecules. When you eat your food, what are the major food categories you eat? So if you ever try to go on a diet, and it depends on which diet you go to, they say eat carbs or don't eat carbs, right? Which is carbohydrates, basically, number one. Eat fat or don't eat fat, right? Which is basically lipids or fat. So you can put the word fat here. And then the other one is protein diet, which is becoming kind of relatively popular nowadays. So eat protein, huge amount of protein, or don't eat proteins, right? So if you look at your diet is 3 of the major food or organic molecules that basically makes you who you are. So carbohydrates or carbs, lipids or fats, and then proteins. The last group, which is nucleic acid, can be found in everything basically. So if you're eating a piece of meat, that piece of meat is going to have nucleic acid, which is basically DNA. If you're eating plants, you will have a DNA of that plant present inside of the food, which is basically nucleic acid. And I'll go into a little more detail about that in just a minute. So let me ask you guys this before we actually jump into our actual understanding. Let me ask you guys, if I say, give me examples of carbohydrates, what would you type? What would you write? So give me examples in your chat box. What are carbohydrates? Potato, bread, rice, correct. Pizza is a complicated one. Grain, yeah, pizza has a lot of other things in it too. So in a simple version, what else? Same thing with cake. So pasta, and you're just talking about pasta itself. Donut has a lot of other things in it too, including fat. So potatoes, right? I don't know what cassava is. I think I missed that one. Watermelon, that's a big one. French fries minus the oil. A starch, correct? So one thing that I really want to highlight here for you guys, and I think like part of you guys get that, but the other part is you get part of the carbohydrate, but not the second part. When I say carbohydrate, you guys only thinking about, and based on your answers, and that's what I'm basing it on. You're only thinking about things that are considered things that help you gain weight or cause weight gain, basically. So things like potato, rice, bread, pasta, right? Grains, things that are kind of ingrained into our brain as carbohydrates, right? But the other side of the carbohydrates are basically your fruits and vegetables. So a lot of times I ask my students, what is fruits and vegetables? And many people say, proteins. And I'm like, no, but just think about it. If you are eating fruits, what is the taste of your fruit? They're sweet, right? Why are they sweet? Because they contain sugar. Sugars are not fat, right? We already know that, right? So when you're eating sugar, sugars are carbohydrates, right? So kind of think about it in that sense. So when you're eating fruits or vegetables, let it be lettuce, apple, grapes, watermelon, anything, those would be your carbs, correct? Your carbohydrates, your sugar. So when you're thinking about carbohydrates, think about it as 2 major categories from what we eat as humans. Yes, well. So when we're eating carbohydrates, one part of it are things that are typically we say is bad for you. You know, if you eat too much of it, it's going to help you gain weight, like bread, pasta, potato, etc. Right? And the other side of this is the healthy carbohydrates that we encourage, especially our kids, to eat and ourselves, because they're rich in vitamins and minerals, etc. Those would be your carbohydrates that are fruits and vegetables, right? So don't dismiss the fruits and vegetables as they don't fall into any of these categories. They're actually a big part of carbohydrates. And hopefully that makes sense to you guys. All right, so lipids, give me examples of lipids, guys. Coconut oil, olive oil, So be more specific. So when you say fat, lipids are fats, but that's not an example. Not oil. Okay, meat is what, guys? Meat is mostly protein, right? Nuts have a lot of, fat in them. So typically I say to my students, basically anything you use to fry things are gonna be lipids or oil. You also can include your dairy product. No bread, right? Bread is not, we just talked about bread. Bread is what, guys? Bread falls under what category? Carbohydrates, right? So lipids, the easiest way to think about it, guys, is things that are coming from animals or coming from plants that are, we as humans use them for mostly frying, right? And the other thing is that it also makes your food taste really good. And I always tell my students, a lot of times the food that you eat outside, one of the main reasons that it tastes better than the food that is home cooked is because of the amount of fatty food that they use, or sorry, the amount of fat or oil they use, which basically makes the food taste so much better because it works with something called the umami taste, or making the food savory. Tacos. Again, so I want to make sure you guys that you understand when you're giving me example of the actual food. Food is not one thing, right? So if you're choosing something from a menu in a restaurant, they're usually going to contain all three food categories, which is carbs, lipids, and proteins. And to kind of clarify that for you guys, I always use if you ask me what's my favorite food that you can't live without, is mine is burger. So if you look at a burger, let's say a typical burger has your bun, lettuce, tomato, the mayo or the sauce, and then the cheese and the meat, right? Your patty. So in that case, don't start me with farmer's boys. So the patty would be your meat, right? The cheese and the mayo mostly going to be your oil or your fat. And then your bread, your lettuce, your onion, your tomato, your pickles, all of those would be your carbohydrates. So understand that when you give an example of a food, it's not one item or another, right? It's usually when you get a food as in a restaurant, you're getting all three categories of the food. The difference is which one is going to be at a higher percentage. Is it going to be a fatty food that's mostly oil, right? Like a cheese stick, right? Or is it going to be, I guess a salad, right? A chicken salad, which has proteins and carbohydrates in it with a little bit of oil. So make sure you guys make that distinction. Hopefully that makes sense to you guys. Okay, in terms of proteins, guys, what are the source of proteins? Again, be specific based on the example I gave you. Turkey, beans, tuna, fish, bread, perfect. You guys got it. Meat, chicken, all of these are identified as a main source of protein for our body. And again, if you're a vegetarian, the main source of your protein will come from beans, correct? Legumes are going to be the main source of proteins for you. I don't know what, if there's anybody that's vegan that has, pinto beans are really high. What is the source of protein in a vegan? My best friend is vegan, but I just don't like the diet, so I never ask about it. Eggs are big. Yes, eggs are huge in terms of protein, correct? Chicken breast, yes. So tofu, yes, thank you. Tofu is a big one for vegans, correct? You got it. I remember this now. Just my brain, I have pregnancy brain, so. Okay. Oh, jackfruit has proteins? I didn't know that. It smells disgusting though, sorry. Yeah. Okay, so the last category which we're going to talk about is nucleic acid. And again, I'm not going to go into detail about that. We're just going to kind of leave it until we get to the end of the PowerPoint. Okay, so you guys are funny. All right, so let's just start and briefly go over each of these 4 categories of food. So organic molecule, the main one would be carbohydrates. And again, guys, please, 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 I am telling you and I'm begging you to understand this right, because these are literally your exam questions. And I don't want you guys to kind of misunderstand the information and don't do well in your exam. So I'm telling you, these are exam questions. So if I ask you guys, what's the job of carbohydrates in our body? The easiest way to think about it is source of energy or short-term energy storage. So be careful with the wording, guys. Source of energy is in terms of glucose. So you know how if somebody is like they feel dizzy or they haven't ate or they're fasting, they get dizzy, right? They get lethargic, they are tired, right? They feel sleepy. So all of these happen because their glucose, which is the main source of energy for the cell and the activity in their body, is low. There is not enough glucose circulating in their bloodstream, correct? So glucose level is low. What is glucose? It's carbohydrate. So when you're thinking about source of energy for your body, you don't go to lipids, you don't go to proteins for it. You go directly to glucose, and glucose is going to be basically what your body taps into to basically function, right? And hence, if somebody is diabetic and that glucose balance is off, they're going to have major health issues. And a lot of people, and I want to make sure this is clear as well, and you go into physiology a lot more about this. When you talk about somebody being diabetic, I don't know if you know anybody or yourself is a diabetic, it's not just a matter of your glucose going higher than normal. You could also have the opposite when you get too much insulin and your glucose level falls below normal. So you can have two either extreme cases. And that's why it's important to, before you take a sip of glucose, you know, if a person is diabetic, before you take a sip of the glucose, they might actually be low in glucose or high in glucose. So you have to always measure your glucose by doing that tap with your finger, get a drop of blood and measure your glucose before you either eat anything or get insulin. So the second thing I want to tell you guys is, so it's not you eating glucose, but if you eat vegetables, right, which a lot of food was supplemented by it, it does contain carbohydrates. And I'll come back to this in just a second as well. So the second part is short-term energy storage. So when we're thinking about glucose, so let's say you ate a piece of bread, and just this is an example, again, arbitrary numbers. You ate a piece of bread. Let's back. You ate 2 pieces of bread, okay? But at that time, your body only needed 1 piece of bread, okay? In terms of glucose, in terms of source of energy, it only needed 1 piece of bread. So your body says, okay, I have some glucose left in my bloodstream, but I don't want that in my bloodstream. I want to store it. I want to save it up for later. So when I save it, then it would become what? Here's the keyword, guard: short-term energy storage. Short-term, the keyword is short-term, which means if I'm running low in glucose, I'm going to tap into that source. Now, what is that source called in humans? What is that short-term energy stored in humans called? It's called glycogen. And yes, you're correct. I was just looking at the thing. That's called glycogen, correct? So if I take, and I'll show you this picture so you guys can get the picture. If I look at this image, and this is a single glucose molecule, right? This hexagonal structure. If I put hundreds upon thousands of these glucose molecules together, what I form is this molecule called glycogen. So see, many, many hexagons together. If my body doesn't need that extra glucose, it becomes glycogen. So it goes this way. So the direction is this way. But what if I didn't eat for like 10 hours? Your body is going to say, ooh, I have all of these glycogen. So what I'm going to do, I'm going to break it down to what? Back to glucose and use it as a source of energy. So a common misconception is this, that, okay, I'm low in glucose, so I'm gonna tap into my fat. Your body doesn't tap into the fat immediately. It first taps into the glycogen. And when that short-term energy storage is done, I don't have any more of it, then it's gonna go into tapping into the fat and lipids as a source of energy. Okay, does this make sense so far, guys? Any questions? Okay, awesome. So let's look at some of the vocabulary that's associated with your carbohydrates. So carbohydrates, we have the simplest version that I already talked to you guys, which is glucose, immediate source of energy, right? That is called monosaccharide. Anybody remember what mono means? M-O-N-O, what does that mean? One, monosaccharide means one. So monosaccharide means one. So you're basically talking about one single glucose molecule or one simple sugar molecule, which is what I have here. If I put two glucose molecules together or two simple molecules of sugar together, I get what? Disaccharide. Di means what, guys? It's kind of self-explanatory, correct? So disaccharide means two. So disaccharide, the best example of disaccharide would be maltose, which is basically putting two sugar molecules together to basically make your, disaccharide. So if you go back to the example that I have here, notice you have, again, one glucose, two glucose, they come together. So this is what we're depicting here is a maltose molecule. Now, going to the third one, what is the word poly means to you guys? Anybody knows? More than two is like really at the lower end. So poly usually means multiple or many, correct? So we're not limited to two. So if you look at the examples that I gave you, look at them. There are quite a few of them put together for the polysaccharides, correct? So exam question, guys. When you're thinking about polysaccharides, one of the things that helps you distinguish the different types is, are they from animal or are they from plants? Okay, are they from animals or are they from plants? We talked about them in terms of animals, right? Animals like us, like if you eat cow, sheep, salmon, etc. The way they store that glucose is in a form of glycogen. In terms of plants, here's the keyword, guys. In terms of plants, they have two ways of storing it. Not just one way, two different ways. One is in a form of a starch. Can you guys give me examples of the starch? What is the starch? Potato, pasta, rice, all of your grains basically, right? Correct. So can we consume those and get energy from them, guys? Can I consume potato and get energy from it? Correct. Yes. Yes. Makes sense, right? If I eat a potato, it's a good source of energy for me. In many countries, it is actually one of the main source of energy for them. The second thing is fibers, guys. Fibers, also called cellulose. I'm going to type it in the chat box for you guys. So cellulose, what is fiber or cellulose? Where can you find fiber and cellulose, guys? Fiber or cellulose, I guess I should say. It's still in plants, but more specifically, what type of colored plants are going to be super high in it? Green, yes. So when you guys hear the word fiber, more specifically insoluble fiber, those are what we call cellulose, and they're identified as insoluble or things that our body cannot break down as a source of energy. Okay, our body cannot break down fibers as a main source of energy. So what happens is basically when you eat green leafy vegetables, right? Those are basically gonna go from your mouth all the way to your butt or your anus and clean your digestive system, correct? They're going to help you clean your intestines. So when you're looking at the two main different type of polysaccharides that are originating from plants, okay? We have a starch, things like potato, rice, pasta, which I'm going to use as a source of energy. Or we can have things called fibers or cellulose, which what the purpose of it for me to eat them is to help me clean up my digestive system. And yes, a lot of people, it mentioned that it slows down digestion. It kind of fills you up and your body's like, let me see if I can break this down, right? So it kind of slows down the kind of the digestive process in a good way, not in a bad way. So it makes you feel full for a longer period of time. Does this make sense to everybody? It does help with the blood sugar level as well, yes. So if I ask you guys this, you're eating a piece of meat, okay? What type of polysaccharide can you find in it? What would you say? You're eating a piece of meat, what type of polysaccharide would you have in it? Glycogen, you got it. Let's say you're eating lettuce. What type of polysaccharide is most common in lettuce? Fiber, correct. So hopefully that puts you kind of give you an idea of what the differentiation is gonna be. So let me show you this picture. Let's go back to the picture that I showed you earlier, guys. Look at the structure of both a starch and glycogen. Okay, see how similar they are to each other? That means that if your body can break down glycogen that it produces itself, it can probably break down a starch too, right? Because their structure is so similar to each other. But look at the structure of cellulose, guys. It's completely different, right? So can you imagine your body breaking this down? Chances are probably not, right? And hence it just goes through your digestive system. Can a sheep or a cow break down cellulose or fiber? Correct, because they have the proper tool, what we call enzymes, to break down cellulose and use it as a source of energy. Yes, that's one of the reasons the cows have 4 stomachs. It takes the time for it to break down. It's just more difficult. And yes, one of the main reasons that it is difficult is not only the type of the linkage that you have, which is really important, but also that the linkage, the number of linkage is more numerous as well. So the more linkage it is, it's more difficult for the body to break down. Any questions about this, guys? And hopefully I didn't miss any questions that you guys typed in your chat box. If it is, just retype it and I can answer that. I haven't had breakfast. My breakfast has been tea, so no complaining. And I can get up and go eat something, so go get something to eat. What is Porto's cakes? I have no idea what that is. So is that supposed to be a bakery? I don't know. Oh, it's like a famous bakery? Okay. Clearly, I did not know that. I bake my own cakes. Okay. Not sidetracked. We're just talking about sugar and how bad that's a bad sugar and we can't eat that, guys. Okay. So the second category of food that we have is organic molecules, which we know as lipids. So first of all, let's make sure that the word that we use is correct. So when we're talking about oil or fat, okay, both of these are under the umbrella of lipids. The difference is when we're using the word oil, it basically originates from plants. So it's mostly going to be liquid. And yes, there is exceptions like coconut oil that is going to be solid at room temperature. But if you're using the word oil, typically it means it's coming from plants and it's liquid at room temperature. So other examples is like your canola oil, right? Your grapeseed oil, your avocado oil, all of these are going to be oil. Not necessarily, it's not necessarily the means it's processed, it's the origin of the oil. So yes, typically if it's from animals, like things like lard, We call them fat, and they're not as processed. But if you're eating butter, it's technically processed there. Okay, so let's think about our body. Again, our goal is to look at what our body produces, not what plants and etc. produce. So when we're looking at our body, the most common, again, typical exam question, guys. What is the most common type of fat we have in our body? What is circulating, what fat is circulating in our bloodstream as a main way of us storing energy and again, using it to survive? And that would be a type of fat called triglyceride. Adipose is just basically, it's a generic term called fat. So the type of fat we have in our body is triglyceride. If you have ever done blood tests, guys, one of the things that your doctor measures is what? Triglycerides, right? Which is also comes if you're doing the blood panel. They also measure your LDL and your HDL, which is your good cholesterol and bad cholesterol. It's correct. Well, we don't go into that. Hopefully, you'll talk about this later on. And yes, it is called lipid panel, which is really important in terms of your health and your risk of having disease such as cardiovascular disease, heart attack, stroke, etc. So question is, what is this triglyceride? What is this triglyceride made up of? So triglyceride, which is again, fat that we find in our body. We're not talking about plants or other animals. The type of fat we find in our body, the way that our body processes fat, is going to be triglyceride, which is 3 fatty acid chains, these 3 boxes of horizontal boxes you see called fatty acid chains. And there's 3 of them, hence the word tri means 3. And then the backbone you see right here, which is glycerol. So backbone is glycerol, and then you have 3 chains of fatty acid in front of it. And then as a whole, that forms your triglyceride. Does that make sense so far, guys? So we're not concerned what the fat from outside coming into our body, but how does our body convert that fat and stores that fat? And that fat is triglyceride. It's not a good thing. Gotta eat healthy. Now, here's the thing, guys. A lot of people, if you talk to them, they kind of assume, especially if they're kind of health nuts. Sorry, no offense if you are one of them. But a lot of people assume that when you eat fat, fat is going to be bad for you. But please do note that fat is one of the main things for our body and necessary for our survival. So I have provided you with some example here in terms of function. So long-term energy storage, guys. Remember, long-term versus short-term, right? Short-term were carbohydrates like glycogen. Now long-term. So let's say go back to the example of the piece of bread that I gave you guys. So let's say in this example, you ate 3 pieces of bread, okay? So the first one was glucose in your bloodstream. The second one was stored into your short-term energy storage as glycogen. The third piece of bread, you said, okay, I definitely don't need this for a while. So what am I gonna do? I'm gonna store it for long term, for much later on. If my body definitely starts to need it, then that long-term energy storage would be in a form of fat. I wanna just kind of add this because this is some of the most common misconception I see among my students. They say, well, I consumed a lot of carbohydrate. I ate a lot of bread. Why am I gaining weight? Or I ate a lot of proteins. Why am I gaining weight, right? So understand this, guys. This is really important. You go to a lot more detail in physiology for it. Anything your body doesn't use, yet it be carbohydrate, yet it be extra lipids, or yet it be protein. If you eat these 3 categories of food and your body doesn't need that immediately, it will get converted to fat because fat is the most effective way of storing it. I'm not going to go into details how it does it. There's literally a significant process. There's a lot of biochemistry that's happening in terms of changing the molecule. But understand that if you eat too much carb, if you eat too much protein, if you eat too much fat, regardless of which group of food you eat, you're still gonna gain weight if you're not using that energy effectively. Does that make sense? I had a person that comes to me a while ago, like years ago, and he says he was trying to basically build muscles, and he said, I'm eating all of these protein shakes, and nothing is happening to my body. I'm just gaining weight, and I'm like, so what do you do other than eating those protein shakes? And he says, nothing. And I said, for building muscles, what do you need to do, guys? You need to what? Work out. You need to exercise, correct? You can't just eat and just hope for that to become muscles. So yes, you do need to exercise and work out. Not necessarily cardio. The best way to gain muscle mass is resistance training, basically weight training, correct? Cardio does help with muscle, but not as much as resistance training. But you cannot do one without the other. So if you start to if you're normal weight, you're not overweight, and you start to exercise significantly, you're just gonna get tired because you don't have the source of energy. But if you are trying to build muscles, you have to increase your protein intake and then exercise and do resistance training side by side, basically. Okay, so let's look at the next example. Insulation against heat loss. Say it again. So if you are trying to build muscles and you don't have extra weight on you, so you're within the normal body limits, the best way to help it is increase your protein intake and then do resistance training if you want to build muscles. If you are overweight and trying to build muscles, you still do need to increase your protein intake, but you need to have significantly high level of exercise. And it's amazing how fast your body converts that extra energy and extra deposits of fat into muscles. So it does work. Yeah, I don't know about that. So okay, insulation against heat. So underneath your skin, there is a layer of fat, and that layer of fat is basically your insulation. The thing is as a person ages, I mentioned that last time, I think, as well, as the person ages, that layer of fat is slowly disappear. And the main reason that you see a difference between you and around when you're around an elderly and they're kind of like wearing like 10 layers of clothing and you're just walking around a t-shirt is because that older person has lost that insulation. So they're continuously losing heat to the environment, versus you have that insulation, so your body can store that heat. There is layers of fat. This is normal, healthy fat around your heart and kidneys as a level of protection. The membrane of your cell, and we'll talk about that today as well. The membrane that's found around your cell is called a phospholipid structure. And basically every cell, the trillions upon trillions of cells that you have in your body, have this cell membrane, and therefore they do need lipids to maintain that membrane. And then somebody mentioned that the importance of lipids for women. Yes, it is important for women, also for men, because what you see in terms of cholesterol, again, a lot of people, when you hear the word cholesterol, you immediately kind of go into that negative place and it's horrible, it's bad. But in reality, if you look at the picture I have here, you have your cholesterol up here, and then you have the two main sex hormones for male and female, which is testosterone and estrogen. And you can see the similarities between the structure of cholesterol. So a lot of times when people go on diets and they eliminate fat from their diet, unfortunately, what happens to them is they have a significant decrease in their sex hormones. So women may see differences in terms of their menstrual cycle. They may have difficulty getting pregnant if they're trying to do so. Male, their sex drive goes down, their muscle mass goes down. So a lot of things can happen if testosterone and estrogens are out of balance. Yes, the myelin sheets also around the nerves does contain fat, but we'll get into that when we talk about nervous system. It's not fat itself. There's cells that have fat around them. So, but that wouldn't make sense until I actually talk about that. So there are actually cells that are wrapped around the nerve cells called are they oligodendrocytes, or they called Schwann cells, and those cells have fat inside of them. But we'll get to that. Any question about the functions, guys? Don't laugh at the picture. It was a 7-Eleven picture. I thought it was funny, so I posted it. Okay, so let's go ahead and continue with our fat and what we need to know for our lipids or fats. So you probably have heard of these three types of fat. We have what we call saturated fat, which a lot of people identify as unhealthy. These are the type of fat you can find in butter or fats that are originating from animals. Yes, they are bad fat, but they are not the worst type of fat that we can consume. And I'll talk about that in just a minute as well. So when you look at this type of fat, which is saturated fat, what you have, if you go back to the picture we had earlier, so notice right here, you have a lot of carbon and hydrogen, right? So notice how the bonding between the carbon and between the carbon and carbons. So carbon, 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 carbon. See how there's that single line? So that means there is a single bond or chemical bond or covalent bond connecting one carbon to another. So I'm going to repeat this. The connection between a carbon and a carbon is a single covalent bond. Why is that important? Because when you have that single covalent bond, you will not have any double bond, and every other possibility of the bonds are filled with hydrogen, or it's saturated with hydrogen. Look at the word, guys. Saturated fat, saturated with hydrogen. Now, when you look at this structure, when you're saturated with hydrogen and have no double bond, the structure that is created is a straight structure, like what I show you here. See, it's a very straight structure. So why is this important? When you have this beautiful straight structure, it's really easy to pack the fat molecules on top of each other. When you pack so many molecules in a very small space, basically your molecule becomes super dense and it's going to be solid at room temperature. Again, guys, typical exam question. What are characteristics of a saturated fat? Saturated fat has single covalent bond between carbon and carbon. It is saturated with hydrogen. Because it's such a beautiful straight structure, it is easily packed and therefore solid at room temperature. Okay? So whatever I just said for saturated fat, reverse it for unsaturated fat. Okay? Which means you will have double covalent bonds between carbon and carbon, right? So instead of having a single line going between them, you have another line right on top of that. So you have double bonds. If you're double bond, are you going to be saturated with hydrogen? Yes or no, guys? No, correct. So unsaturated, literally the word unsaturated means what? You're not saturated with hydrogen. So is this the structure going to be straight? So again, reverse everything. The structure is not going to be straight. It's going to be bent. It's going to be crooked. So it's not going to be easily packed, which means it's going to be what? At room temperature. If it's not solid, it's what? Liquid, correct. So think about your typical oil coming from plants. They are there is liquid at room temperature, which means they are going to be the healthier alternatives compared to saturated fat. So somebody mentioned earlier in the chat box that saturated fat are easier to break because they have single covalent bond, and that is correct. So if your body gets saturated and unsaturated fat, saturated fat, the structures is simpler, it's a straight, it's nice, it's neat, so it's easy for your body to break it. Unsaturated fat, because it's crooked, the structure is not straight, then it's harder for it to break, it's harder for your body to break it down. And therefore, it takes longer for your body to break it down. So if I say among the two fats, which one is the healthier for you to consume? You will say what? Which type of fat is better for you if you are to consume fat? Unsaturated fat, correct. Because first of all, it's no LDL. LDL has nothing to do with this right now. We're just talking about the difference between saturated and unsaturated fat. So unsaturated fat is better for us because of the double bond. It makes it harder for your body to break it, so it takes longer for your body to process it. So any type of fat, so the question is an example of long-term energy. Any type of fat in our body or any type of fat sources is identified as long-term energy. It doesn't matter if it's trans fat, unsaturated fat, or saturated fat. As far as the word fat, lipid, or oil is in front of it, it is identified as long-term energy storage. So there's two different concepts I'm presenting here. What is the function of the fat in our body, right? And then which one of the fats that I consume would be the best type of fat for me to consume, okay? So doesn't matter what they do, they're all gonna do the similar job, but in terms of my long-term health, which one would be the better one to use? Good, I'm glad you're learning. Okay, so the third category that we have, well, I'm gonna talk about trans fat. So trans fat is a whole different ball game, guys. So trans fat is actually identified as the most unhealthy type of fat that you can consume. Okay, so I'm gonna say it one more time. So if you're looking at the three categories of fat, which is saturated fat, unsaturated fat, and then trans fat, between these three, which one is the worst type of fat? Your answer is trans fat. And then trans fat, why is it so bad, first of all? It is not something that you can naturally find in your environment, okay? So it's not like, oh, I'm gonna go get, an avocado and then open up the avocado and check for the fat, and it's gonna be trans fat in there. You cannot find trans fat in your normal body. And I don't wanna use the word process because yes and no, that's not true necessarily. So trans fat can be processed. Yes, that is true. It can be man-made. It is much cheaper. It is important in terms of the fact that it can be heated and reheated over and over again and having a stable structure. So it has all of those characteristics. But what makes the trans fat really dangerous, and I really want you guys to understand this in terms of your health and your family's health, is trans fat originally was created because people were worried about their health. And I said, okay, we're consuming way too much saturated fat, like butter. Like, before, if you were going to do cooking or baking, you would just use pure butter. And I said, okay, new research is showing that butter is really bad. And we're talking about 1970s, 1980s. So they started doing research and said, okay, we're gonna come up with a new fat that's gonna taste better. It's gonna be able to be reused and it's cheap. And because this is a new type of fat and your body doesn't know what type of fat it is, what it's going to do is you're going to consume it, you're going to enjoy your food, and then your body's going to let go of it. So you're basically going to poop it out. Your body's going to remove it from your system. What happened in reality within 10 years of introducing trans fat in terms of our baking and in terms of our cooking, fast food especially. The number of heart attack went through the roof. And there's a YouTube video that I posted for you guys. It is an old video, but it still kind of highlights the whole idea. The number of heart attack went through the roof. And the main culprit in that one was trans fats. So what happened in reality is your body got trans fat into the system and it said, I don't recognize this. But instead of getting rid of it, your body is a hoarder. So what did it do? It stored it. It puts it inside the body. So where did it keep it? Inside your blood vessels. So blood vessels of the heart became clogged, blood vessels of the brain become clogged, and you become susceptible to heart attack and strokes. Okay, so that's why trans fat is so dangerous, because you cannot, basically your body cannot process it, but it holds on to it. Other type of fat, even if it's saturated or unsaturated fat, you're still gonna be okay because your body has the ability to process it. Would a huge amount of fat in general be good for you? The answer is no. But if I say which one is the worst type of fat, you still have to have trans fat or avoid trans fat. Going back to the earlier thing that the person mentioned, Brenda mentioned, it says processed fat. No, it doesn't have to be processed. It's, if you, let's say you take olive oil, for instance, okay? And you're cooking and you heat that oil too high. So you pass a certain temperature, and I don't know what the temperature is because I don't use olive oil. When you pass that temperature, your regular oil will get converted to trans fat. So increasing heat, reusing the oil that is not supposed to be reheated. All of these are really bad because it literally changes the structure of a healthy oil to a trans fat. That's why when you bake, you need to be very careful with the oil, especially if you're using oil. I'm not talking about butter, but if you're using oil in terms of your baking or your cooking, to know what is that temperature that converts it from regular oil to trans fat. Okay, so it might not convert every single molecule of that fat to trans fat, but there is a change in the structure that can cause significant damage. So the best oil, if you are to, it does have effect on butter, but again, you're thinking about unsaturated, because saturated already has all of its places taken up by hydrogen, so you cannot add more hydrogen to it. So it affects it affects unsaturated fat, not the saturated fat. So when you guys, let me just clarify this. When you guys are using oil for frying things like deep frying, the best oil, and I learned that recently, the best oil that is in the market and it's extremely expensive is rice oil. And rice oil can be heated and reheated multiple times without it being converted to trans fat. So if you are a big fan of doing that, like doing deep frying, the best oil to use is rice oil. And it's expensive, trust me. The regular bottle is like $20. But if you are thinking about your health and you shouldn't be eating too much deep fried food anyway, but if you are to reuse your oil, invest in rice oil because it doesn't change its structure when it gets reheated over and over again. And it has a very high boiling point. So it takes a while for it to actually get converted. Avocado oil is the same thing. You cannot reheat and reuse it. The best one in the market, based on the studies, and again, this is recent studies, is rice oil. I really don't recommend reusing any other type of oil for reheating multiple times. That's my recommendation. You guys can go do your own research and figure it out, but I would avoid it as much as you can. Yes, so I don't know what that means. Most countries in Europe praise fat. I don't know what that means, sorry. But in terms of what you guys are asking about peanut oil and avocado oil, honestly, go do your research. But in general, if you're looking at reheating the same oil, either think about it as a animal oil that is basically saturated fat, not the typical liquid oil that you guys use, because that can cause it can significantly change and cause damage to your body in long term. So again, don't assume just because I didn't eat outside and I fried my own food, you're good. So, okay, one last thing before we take our break, because I've been kind of going over that thing. So good versus bad cholesterol. So I want to make sure this is clear, guys. There is nothing called a good cholesterol and a bad cholesterol in terms of cholesterol. Cholesterol is just a molecule. What we identified as a bad cholesterol is low density lipoprotein, or LDL. So in a blood test, you usually see that as LDL. Bad cholesterol is carriers of cholesterol. They're not cholesterol themselves. They're like taxis that take cholesterol in and out of your body, okay? HDL are also taxis, which are called good cholesterol or high density lipoprotein, or HDL. So what is the difference between LDL and HDL? So LDL, make a note for yourself, as this is again an exam question. LDL is going to take cholesterol from your organs like your liver and send it into your bloodstream, which means that cholesterol that is now in your bloodstream can clog your arteries and can cause heart attack and a stroke. So if your bad cholesterol, or LDL, is high, you're at the higher risk of heart attack because you have more fat in your blood vessels. HDL are the good taxis. What they do is take the cholesterol from your bloodstream and send it back to the liver. So their job is to basically cleaning up your blood vessels. So it lowers the cholesterol that is circulating in your bloodstream. So when you're saying high cholesterol versus high LDL versus HDL, LDL, what it's doing is adding cholesterol into your bloodstream, and HDL is taking that cholesterol away from your bloodstream. One quick note on that. LDL is directly related to the fatty food that you consume. LDL is the one that is directly connected to the food you consume. So the more fatty food that you consume, the higher your LDL, which means the more bad cholesterol, and I'm going to put that down, the more cholesterol you have in your bloodstream, and the higher your risk of cardiovascular disease like heart attack. HDL, the best way to raise up your HDL, which is the good cholesterol, is exercise. Exercise helps raise your cholesterol. It doesn't necessarily have to do with your diet as much, but one thing that you can do is exercise. And again, that HDL is going to take that cholesterol away from your bloodstream, take it to your liver for storage, and basically keep your blood vessels clean. Oh, thank you, Dana, for clarifying that and typing that. Any question, guys, before we take a break? Because we're going to go to protein after that. Awesome. So right now is 9:23, so please be back by 9:40. And then we'll continue afterward, okay? I'm going to stop the recording for now. So we have talked about two of the groups so far. So we have talked about our fat as well as our carbohydrates. So let's talk about the third group, which is going to be our nucleic acid. And I put nucleic acid ahead of proteins because there is a connection between the two. So that's why. So when we're talking about nucleic acid, if you're looking at nucleic acid, it's a gigantic molecule, kind of like when you look at glycogen, it was many, many sugar molecules. So nucleic acid is the same way. So if I look at this gigantic molecule that's made up of many, many tiny units, Those tiny units are referred to as nucleotides. So thousands upon thousands of nucleotides make your nucleic acid. So I just want to make sure that relationship is makes sense. Now, when you look at what is the function of nucleic acid, the main function of nucleic acid is to store your genetic information. So I think everybody has an understanding when you say nucleic acid, which are basically things like DNA or RNA. The first thing that kind of pops into your head is like, well, I get that from my parents, it makes me who I am. It gives me my eye color, my hair color. It's if there is a problem, then I might get sick, things like that. So things are very generic understanding of nucleic acid. So all of the things that I mentioned are correct answers, but it doesn't answer why do I even care to get genetic information from my parents? Why do I need that in the first place? So the question, the reason, and this is really important, again, typical exam question. Why do I care about nucleic acid? It is because it tells me how to make proteins, okay? So it's not important that it comes from my parents, okay? It doesn't matter that I do share that information, but the main reason nucleic acid is essential for us is because it basically gives us the direction of how to make proteins. And as I said, proteins is another main groups that we have, and I'll talk about that in just a minute as well. So please understand that if you give me the answer in an exam, or I think in one of your Canvas posts that says, it's always stored genetic information is from my parents, etc., you're not going to get full credit. The answer I'm looking for in terms of the importance of nucleic acid is that it is the guideline, it is the blueprint for me how to make proteins in my body. And proteins are basically what do all the functions in my body. The actual action, the actual function, the actual chemical reactions are done by my proteins. Another importance of nucleic acid, other than the fact that it's genetic information and helps me with protein production, is this molecule called ATP. ATP is the way your body basically uses energy. So I want to make sure this is clear. So when you look at a cell, so this is your cell, okay? So what your cell does, what comes into your cell is glucose, okay? So glucose comes into your cell, which we already talked about is the main source of energy for your cell. Now, how does your cell uses the glucose? That's the question. That's the next question. So how does your cell uses the glucose? It goes through a process, through a bunch of chemical reaction, and it takes that glucose and converts it to ATP. Okay, so glucose through many chemical reaction becomes ATP. Yes, it is glycolysis is a very small part of that process. There is actually Krebs cycle and electron transport chain, which we're not going to get into that. Glycolysis, all it does is the first step in a multi-step process. So when I ask you guys, what is the main source of energy for your cell or for your body? The answer is glucose, okay? But how does that cell use that glucose? Is it actually converts it to ATP for all of its chemical reaction. And if I ask you, what is ATP categorizes as? The answer would be nucleic acid. It's not carbs, it's not a protein, and it's not a lipid. So the only option you have is nucleic acid. So here is basically a little bit more about the DNA and RNA and ATP. So first of all, if I ask you what is DNA stands for, it stands for deoxyribonucleic acid. So the D and the N and the A I highlighted or bolded it for you. RNA stands for ribonucleic acid. So what if I compare what my DNA looks like compared to my RNA? And I'll talk about why we have DNA and not all of them are DNA or not all of them are RNA. So the two main category of nucleic acid, I'm just going to repeat this one more time. The two main categories of nucleic acids are DNA and RNA. The differences, if I say, and again, typical exam question, what are the differences between DNA and RNA? And I really like this picture because it kind of highlights some of the main differences. First of all, DNA is two strings or two strands connected. So it forms that kind of beautiful double helix that we have. So DNA, for our purpose, for us as humans, they're always going to be double stranded. And yes, it says few exceptions, but not in case of us. As humans, we're always looking at double stranded versus single stranded. So RNA would be my single strands. Again, in my body, there are exceptions in terms of microbes and bacteria and viruses that may have differences in that term. The second difference is nucleic acids, DNA and RNA both have a component of sugar. The sugar that is forming in our DNA is called deoxyribose, and the sugar that is in my RNA is called ribose. So ribose, take the ribose, see how they share both the ribose, and I have the word deoxy in front of it. You remember what is the word DE means? D? What does that imply? Not die, D. Die is DI, this is DE, correct. DE means without. So make sure you guys can distinguish that. Again, I'm gonna just type it for you guys. So DI means two, DE means without. So make sure this is a difference that you can distinguish. So when you hear the word deoxy, what do you think it implies? Without what? Oxygen, correct. It's without, deoxy means without oxygen. So it is still a ribose, right? It's still the same sugar, but it's missing an oxygen. So if you're distinguishing between DNA and RNA, other than the fact that it's a double-stranded versus a single-stranded, DNA has deoxyribose, which means it has lost one of the oxygens on the ribose. And then RNA means the sugar is just a perfect sugar with all of its oxygens, and it's called ribose. Now, the next thing we have in terms of differences is what we call bases of the DNA and bases of the RNA. So if I'm drawing, and I'm just gonna do a really quick drawing. So if I'm doing a nucleotide, remember nucleotides, and just go back. So when you're looking at nucleotides, which are basically the building blocks of the nucleic acid, a nucleotide is like this, and I'm gonna really simplify it. Let's do something called phosphate, which I really haven't talked about it. Then a sugar. Sorry, I can type. Okay, a sugar, and the third part of this is a triangle, which is a base. Okay, so some people already kind of mentioned thymine versus uracil, etc. But you cannot just say the difference is thymine versus uracil. You need to be specific in terms of what those are. So when I'm looking at the bases that forms my DNA versus the bases that forms my RNA, so those bases that I draw in triangle, okay? The options for the DNA bases are going to be A, T, C, and G. Don't need you guys to know the full name. All you need to know is the shorthand, A, T, C, and G. So if I'm looking at a DNA, the only options I have for bases are these four. If I'm looking for the RNA and the bases found in the RNA, my options are A, U, C, and G. So the difference would be in the presence of a T for a DNA versus a U for RNA. So there are, again, three main differences between my DNA and RNA, and I'm going to repeat it one last time, make sure everybody's on the same page. DNA is always double-stranded for us. RNA is always single-stranded. DNA has a sugar called deoxyribose versus RNA has a sugar called ribose. And the bases that form my DNA are ATCG. The bases that forms my RNA are AUCG. And the difference is T versus U. Is this making sense so far? Any questions? Awesome. Again, typical exam questions for you to distinguish between the two. So one quick note, and I don't have that in the PowerPoint, but I just want to make sure you guys are all in the same page. Oh, no, actually I do have it, so I'll come back to it. So now let's connect the DNA to protein. So we want to say, we talked about DNA, we said that it's genetic information. It helps us as a blueprint for proteins. And now we're going to look at the protein and connect all of these two concepts together. So, so for protein, what do they do in our body? So proteins, one of the most important things that they do. And if you only remember one thing, this is the one you want to remember. Proteins are going to be producing something called, or are, for many of the proteins, are what we call enzymes. So remember all those chemical reactions I talked about earlier at the beginning, and I mentioned things like it's the glue, ionic bond, covalent bond, polar covalent bond, non-polar covalent bond. All of those things, all of those reactions, all of those bonds are formed because I have enzymes in my body. Those enzymes are basically what allows me to create ionic bonds. These enzymes are what allows me to create covalent bonds or break down covalent bonds, okay? So basically, the survival of me as a human being, as a living organism, depends on enzymes, guys. Get that really, it's a really important point, guys. So if I want to survive from second to second, from millisecond to millisecond, I need to have functional enzymes in my body. If these enzymes, for whatever reason, have problems, if they're not doing what they're supposed to do, they're either going to cause major disease for me or they're going to lead to my death in a matter of seconds. For instance, I just want to give you kind of an example to kind of give you a clue. Everybody has heard of cyanide before, right? Cyanide poisoning or cyanide pill that kills in a matter of seconds. What that poison does actually, it targets and destroy, or not destroy, it targets the enzyme that helps you produce ATP. Remember ATP I just mentioned as the energy source? Remember ATP here? So it targets the protein, the enzyme that allows you to make ATP. So if you don't have ATP in your body, you have no energy. Doesn't matter how much glucose you have. If you have no ATP, your body's not going to be functioning. You die, basically. That's why it works so fast. So enzymes are all enzymes. Every enzyme you can find in your body that allows you to do chemical reactions, that helps you survive and live from second to second, are proteins. Hence, proteins are really important. Have you heard of lactose intolerant? You might actually have it yourself. You can eat dairy product, correct? The reason these people have that kind of condition is because they do not have an enzyme called lactase that helps them break down that sugar in the dairy products. So it's either that enzyme is not present, or it's really low concentration, or it has changed and it cannot do its job. So be very, very conscious of why proteins are so important for us. Inability to do something in our body probably can be backtracked to an enzyme. Disease such as Alzheimer's, disease such as Parkinson's disease such as multiple sclerosis. All of these have to do with protein not being able to do their job, or protein doing something they're not supposed to do, or enzyme doing something they're not supposed to do. Lactase. The name of the enzyme is lactase. Okay. So what else does proteins do in my body? They also act as transport. So transport is, best example is hemoglobin, and we'll talk about that later on as well. Hemoglobin is carrying oxygen in our body. Oxygen, we already know. Without oxygen, we won't survive, right? Lipoprotein, remember I mentioned earlier LDL and HDL, those two things that are good cholesterol and bad cholesterol. They're carriers, the taxis that I mentioned. These are actually proteins. So they do the job, they move lipids, but in reality themselves are proteins. How many of you guys have heard of antibodies before? Especially nowadays with this whole COVID, right? Correct. So antibodies, we take vaccination because we want to build antibodies. What are antibodies? Antibodies are proteins. So the defense of our body depends on it. And the one that we usually overlook when we get to this point is our muscles, right? The muscles we have in our body are all made up of proteins, right? So a skeletal muscle that gives me my movement, my motion, are also proteins. Now, let's take a look at this. When I talked about nucleic acid, guys, the gigantic structure that I talked about, which is your DNA and RNA, what did I say those nucleic acid made up of? What are the little units that make up nucleic acids? Anybody remember? No, not ATCG, no. It still starts with the N. Nucleotides, correct. So nucleic acids are made up of nucleotides. And again, I'm gonna go back so you guys can see what I'm talking about. Here, nucleic acids are made up of what? Nucleotides. So same thing applies to your protein, guys. What is my protein made up of? So protein is this gigantic structure. What is the protein made up of? Is made up of exactly 20 amino acids. Different amino acids orient themselves differently. So understand this, guys, that when I talk about proteins, you literally have hundreds upon hundreds of different type of protein, each of those proteins doing different things in my body. So proteins are made up of amino acids, and I make up a protein, then that protein is going to have a very specific job. So the question is, how can I differentiate one protein from another? If I'm looking at protein 1 and protein 2, what makes these two proteins different in terms of their structure? So the difference would be how many amino acids I've used to make them. So maybe one of them only use 100 amino acids to be made, right? And the other one use 1,000 amino acids to be made. So one basically is a small, the other one is large. The other one is, how did I order those amino acids? So did I do 1 amino acid, 2, 3, 4, 5, 6, 7, 8, 9, 10? Or did I do 1, 3, 5, 7, 9, 10, 11? So the order of the amino acid that helped me build that protein is important. And how many of those amino acids did I use to make those proteins? So I usually give my students this example to kind of help you understand it better. So imagine you guys are all sitting in a class and you get a pile of beads to make necklaces, okay? So you have 20 different beads. Each of you guys get 20 different beads, 20 pile of different beads. And I said, student A, make a necklace for me, student B made a necklace for me. Each of you guys are going to do what? Make a different necklace, right? Not a single one of you gonna have a same identical necklace because you guys are different, right? So how many beads each of you guys gonna use is different. Somebody is gonna use 20 beads. Somebody wants to use like a gigantic necklace and is gonna use 100 beads, okay? The other thing that could be different is the order of the color beads that you guys use, right? Red, blue, green, whatever, versus red, 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 right? So the color, then the type of amino acid you use to make your necklace is going to be different. So in an exam, if I ask you the question, what makes one protein? Okay, I'm going to type it. What makes one protein different from another protein? Then your answer would be number of amino acid, and what's the second part? The order of the amino acid, correct. Number of the amino acid and the order of the amino acid. Does this make sense so far, guys? Awesome. So why is DNA important, guys? Tell me, what is the DNA, in my sense, in terms of biology? Why do I care about DNA so much? Because it does what? It doesn't only create enzymes, it helps us make proteins, correct. But I haven't really told you how does DNA help us make proteins, right? So that's the next thing we want to talk about. Good job, guys. So how is DNA related to proteins? So DNA is it's basically segmented or broken down to what we call genes. And you probably have heard of genes, right? Genes is a really common thing that we throw out there. Now, each gene is going to encode for a protein. Now, each cell in our body, again, we have trillions upon trillions of cells in our body, but each of those trillions of cells have their own copy of DNA. It's identical. Every cell in your body has identical genetic information, but you only have, every cell has only one single copy. So what it wants to do, that single cell, what it wants to do is wants to protect its genetic information. It doesn't want to let any harm come to it. But I already know that I need the DNA to make my protein. So how do I still use DNA without putting it in danger of being damaged? So what I do is I make a copy of that gene or that DNA, and that copy is called RNA. Now, RNA is a copy. If you have a copy of something and the original is safe for you, you don't really care what happens to the copy, right? Copy can get destroyed. I don't really care what happens to it. I can throw it away and make a new copy, correct? So in reality, if you're looking at the order of things, guys, like I broke it down for you guys here. DNA is inside a space called nucleus, and I'll talk about that in our next PowerPoint. DNA is going to make its copies called RNA through a process called transcription. Because when you transcribe something, it's what? You're making a copy of it. RNA is going to go out of the nucleus because it needs to be used for making of proteins. And then you have an organelle called ribosome that's going to use that RNA to make the appropriate protein. And that process of using RNA to make the protein is called translation. And again, when you're done with the RNA, when you're done with making your protein, RNA can get destroyed. I don't care. It's a copy. I can rip it apart and it's fine. So as soon as the protein is made, my RNA is going to be thrown away. But again, I always have the original copy if I want to make new copies. Does that make sense to everybody? So please, guys, do not tell me DNA is important because it's genetic information from my parents. This is like the worst answer I literally, if I hear it, I want to rip my hair out. Like it's so frustrating to hear about this. So always remember, DNA is forming its copies, which are RNA, and then the RNAs are going to be used to make the proteins. And proteins do everything in my body. They're the ones that are enzymes. They defend my body. They give me my motions in terms of my muscles, right? So they do everything in my body in terms of functionality. Basically, yes. And so again, here's your DNA, your double helix, right? Here's your RNA as a single strand, and here is my protein. And each of these little orange circles, what do you think these represent, guys? When I close my eyes. Amino acids, you got it. So amino acids are basically what makes my protein. So each of these little orange circles are my amino acid. You guys got it. Good job. So one last concept for this lecture, we still have another PowerPoint, but for this lecture is the concept of acid and bases. And this is really, 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 again, basic. Acid and bases, there are people that can talk about it for hours, but for our purpose, it's really, really, really simple. I don't want to go into too much detail. So when you look at a water molecule, and everybody knows the water molecule is H2O, correct? So when a molecule of water gets broken down, or it goes through a process called dissociation, dissociation means literally pull them apart. You get one hydrogen ion, which is H plus, and you get one part hydroxyl ion, which is OH negative. So water, pay attention to this, guys. Water will have equal parts of hydrogen and hydroxyl ions, 1-to-1 ratio. When something is an acid, instead of having a 1-to-1 ratio for hydrogen ion and hydroxyl ion, you're gonna have a huge number of hydrogen ions. And I mean really large number of hydrogen ions. So the hydrogen ions are gonna be really high and your hydroxyl ions gonna be really low. Base is the opposite. So when a base, something we call a base, gets released into water, it's gonna release a lot of what we call hydroxyl ion or OH negative and very little H plus. So look at the example here again. HCl, for instance, which is hydrochloric acid, is gonna release a lot of hydrogen, and NaOH, which is sodium hydroxide, is gonna release a significant amount of OH. This is a base, that's an acid. Now, have you guys heard of a strong acid versus a weak acid, or a strong base versus a weak base? It all has to do with how much of the hydrogen ion or hydroxyl ion you release. If I'm releasing a huge, I mean like literally millions of hydrogen ions into a solution, that's considered a very strong base. If I'm releasing very little hydrogen ions, that's called a weak base. If I'm releasing huge amount of OH negative, what do I call that? I'm releasing huge numbers of OH negative. What would I call that? OH. OH is what? Base. So if you're releasing a significant number of OH negatives, that's a strong base, correct? And if you're releasing very little OH into your solution, that's gonna be a opposite of strong. It would be a weak base, right? Correct. So I'm gonna repeat this one more time, guys. What makes something acidic is the amount of hydrogen ions. What makes something a base or basic solution is the amount of hydroxyl ion or OH negative. The more of each of those components you have, the more the stronger that acid or base will be. So look at what we call something called a pH scale. pH just basically implies that we're talking about acidity and basicity. So the range for that is 0 to 14. You guys can ignore these numbers. I'm not going to talk about this. So it's 0 to 14. That's the range. Anything below 7, do not include 7, guys. Anything below 7 is acidic, which means it has high concentration of hydrogen ion. Anything that's above 7, again, do not include 7 itself. Anything above 7 all the way to 14 will be identified as correct basic because it has low hydrogen, or you can also write that it has high what? If it's basic, it has high what? High OH, correct, OH negative, or hydroxyl ion. Basic is the same thing as alkaline, correct. So basic and alkaline are the same thing. So if you're looking at this scale that I have here, one thing that you also need to remember is number 7. So 7 is identified as neutral because the amount of H plus and the amount of OH negative is equal, right? That's what we talked about at the beginning. So 7 is considered neutral, is pure water. So please don't say your water is acidic or basic. Water is neutral, and it's basically going to be equal amount of hydrogen and OH at the same time. Does that make sense? So I have a question for you guys. In this chart, based on what I have here, what is the second, take a moment, you're not in a rush. What is the second strong base you have based on this chart? Bleach is the correct answer. So household bleach is the correct answer because I said second strongest, guys, not second weakest. So think about, if you are coming close to 7, are you becoming stronger or weaker? Right? 7 is neutral. So the closer you get to 7, you become weaker, right? The farther you're away from the neutral, the stronger. So the question is, what is the second strongest base based on this chart? Second strongest base on this chart, it would be household bleach, correct? What is based on this chart? What is the weakest acid that I have? What is the weakest acid? Urine, correct, because it's closest to what? Closest to the 7, which means it's in the acid, but it's closest to the 7. And then what is the strongest acid that I have on this chart? Hydrochloric acid is the strongest base because it's basically all hydrogen. Again, 7, somebody mentioned 7 and pure water. Water is pure. If it's pure, it's neutral. It's not an acid nor a base. Is this making sense, guys? So one question for you now. What is the weakest base on this chart? Seawater, correct. Okay, got it. Ooh, trick question. Which of these samples have the highest hydroxyl ion concentration? Which of the sample has the highest hydroxyl or OH concentration? Sodium hydroxide, correct, because sodium hydroxide is the strongest base right here, right? And the strongest base means it has the highest concentration of sodium, sorry, hydroxyl ion. So here, I'm gonna make a notation for you. This is the strongest base based on this chart, right? This one, your seawater, is the weakest base, right? Urine, based on this chart, is your weakest what? Weakest acid, and then hydroxyl. Based on this chart, your strongest acid would be hydrochloric acid. And then again, in terms of numbers, this is going to be the highest in terms of what? Hydrogen, right? Highest in hydrogen. And then this one, your strongest base, is going to have the highest concentration of what? OH, right? Or hydroxyl ion. So one last question, and then we'll finish up with this concept. Based on this, which acid would have the lowest hydrogen ion concentration based on this step? Which acid would have the lowest hydrogen concentration? Urine, correct. You got it, guys. So it's not very difficult. You just have to get practice. Acids are hydrogen, bases are OH. The more of it you have, the stronger that sample is going to be. And then last but not least, buffers. You're going to hear the word buffer a lot when we talk about blood. Buffer is basically what prevents a significant fluctuation in your blood pH or your pH in general. We have a very exam question, guys. Highlight it for yourself. What is the blood pH we have in our system? For us is what we call bicarbonate, which a lot of people kind of, if it's sodium bicarbonate, is basically baking soda. And I don't know why you guys giving me numbers. So blood pH, buffer for the blood pH is bicarbonate, and it's written as HCO3 negative, and it helps us maintain our blood pH. So our blood pH is maintained by bicarbonate. So literally the last bulletin point we have here. What is the blood pH? How do we maintain our blood pH? That would be bicarbonate. If I'm assuming the numbers you guys gave me was associated with what is my blood pH, which is also a number you guys need to know. The number for your blood pH, our human blood pH, is 7.35 all the way to 7.45. That's the normal range for it. Can I underline what? Sorry. So our range for blood pH is 7.35 to 7.45. How do I make sure that I maintain it within that number? I use my buffer. It's the last bulletin point in your thing. So, how do I maintain my blood pH at 7.35 to 7.45? I use a blood pH called bicarbonate, and bicarbonate is HCO3 minus. You're welcome. So is your blood pH normally acidic or basic, guys? Or neutral? No, neutral was a trick question. It's above 7. Anything above 7 would be basic. Even if it's a slightly basic, it is still basic. Yeah, you got it, guys. Is there any question about this PowerPoint, guys? That's about it for this one. Any question, any clarification? Good. Okay, so let me go ahead and open up your next PowerPoint. So you know how like when you guys are trying to do something and your computer decides to do everything else except what you want to do? That's what my computer is doing right now. It wants to update like 20 different things. Like, no, I'm in the middle of a class. No, let's just update PowerPoint right now. No. Technology, right? I'll try to get, we're not going to finish this PowerPoint. I don't believe so. But what I want to really do is to kind of highlight on some of the essential components, and then whatever we don't get through today, we'll pick up next class meeting. So not to worry. I'm hoping everybody can see my shared screen. Awesome. So if you're looking at organizational level, let me ask you this. If you're looking at your organizational level, what is the most basic level of organizational level? You guys better be able to answer this. I don't know, I'll just close my computer and walk away from it. Chemical level, got it. And then chemical level was made up of what and what? Atoms and molecules. Thank you. Okay. You were saved. Okay. So that's basically what we were talking about so far, right? We talked about atoms and we talked about molecules, and the molecules are carbs, proteins, lipids, and nucleic acid. That's basically what we talked about so far. So the next level after we go above that is basically looking at the second level of organization, correct, which is our cellular level or cell. So that's basically what I'm showing you here on this picture. So cell structure is basically, and if you guys have your PowerPoint, can you just tell me if this is the same one you guys have? Is this look right to you guys? I don't know if, okay. Okay, that's fine, but it's the same one though, right? Okay. Just want to make sure. Okay. Sometimes I modify it without updating the new one. So in our cell, we have quite a few structures inside, which is all of the labeling you see around it. That is basically called organelles. And we'll spend most of this PowerPoint talking about those organelles. Yes, your file is in PDF, but it's still the same file, hopefully, in terms of content. I apologize, I forgot apologizing about my voice. Hopefully get better by next week. Okay, so I don't need you guys to know the theory of cell. That's mostly physiology. So you guys basically can ignore this. You don't need to read about it. So I'm just gonna kind of turn on my pen and kind of do this for you guys. So yay, one slide less. Okay, so let's go ahead and get started in terms of what we need to know for cell. So first of all, if you look at the picture that I provided for you guys here, you can see that the cells that we have in our body is pretty diverse. So I gave you some examples like your nerve cells, your sex cells, your immune cells, fat cells, blood cells, muscle cells, etc. You can see they are significantly different when I look at them from outside. But when you look at them from inside, they will contain very specific structures or organelles that are going to be almost identical in all of these cells. For instance, regardless of what these cells look like, they're all, almost all, there is exceptions, they will have a nucleus. They will have mitochondria. They will have rough ER and a smooth ER. They will have lysosome, preoxisome, etc. So it doesn't matter how they will look like this, they would look, they will have the same structures inside of it when I take a look. So let's go ahead and start by looking at what we call basically the breakdown of a cell. So a cell has what we call a plasma membrane, which is basically this kind of clear or I guess purplish color membrane you see around called the plasma membrane. And this is basically sets the boundary for the cell, and it controls what gets into the cell and what gets out of the cell. So it is permeable basically, as in it allows things to get in and out. But the proper word would be it's semi-permeable, as in it allows some things to come in or get out, but it monitors it. It's kind of like border control. It allows people to get in and out through the border, but it doesn't allow everybody to get in and out. Cytoplasm is another word. FYI, anytime you hear the word, and I'm typing that in the chat box for you guys as well, The word site, we already learned, I think, implies cells. Oh, not cute. Change this to cute, sorry. Site. Site means cell. So anytime you hear the word cyto or something similar to that, that implies that we're talking about the cell. So cytoplasm is basically the space you have inside the cell that or contains all of the organelles. So in this, literally, if you have the boundary and the space inside of it is the cytoplasm. And then the last thing you have is this gigantic purple structure inside the cytoplasm called the nucleus. And this nucleus is basically where you can find your DNA and components that helps you make protein. Again, DNA is really important for us. So it has a main organelle that basically protects that DNA and that genetic information for us. So without me going too much into detail about this, this has a lot to do with physiology, not necessarily your anatomy, but I still do want you guys to have heard of the vocabulary. So first of all, when you look at this image, this basically represents your body, guys. So this kind of the box surrounding, that's your skin. So that represents your skin. The yellow stuff represents your internal space, whatever cavities and structures you have. Up here, you can see the gas exchange happening. So what does that represent? What system does that represent? Not just your lungs, but more your respiratory system, right? We're talking about system, we're not talking about the organs, right? Okay, what does this represent, guys? Blood and heart, what does that represent? Cardiovascular system, correct. What does this represents? This on the side. I laugh because it's funny. Digestive system, right? So it's a continuous opening from your mouth all the way to the anus. And then what does this look like? I like the way they draw it because it's kind of self-explanatory to me. Kind of look like a toilet. Urinary system, correct. So you have your main systems. Again, some of the systems are missing from here, but you get the idea in terms of the main system. You have digestive system, respiratory system, cardiovascular system. I know, right? The picture is really cool. Urinary system. And basically, this represents all the cells that you have in your body. So now let's talk about the terms of fluid. So in your body, what is most of your body made up of? Water, correct. 60 to 70% of your body is water, okay? So hence, if you are dehydrated, it can significantly affect your health, and it can actually lead people die from dehydration. So when you look at the water can be found inside your cells as well as outside your cells, okay? So when you look at the fluid that are inside the cell, look, intra means inside. Again, if you're not familiar with the word, I'm typing it here. Intra implies inside. And the word extra means what? Logically, outside, right? So inside versus outside. So intra is inside, extra is outside. So when you hear the intracellular fluid, look at the word, guys. Don't get, oh my God, it's such a big word. I don't know what it's saying. I'm done. Okay, don't think about that. Break down the words for yourself. Intracellular means inside the cell, fluid that is inside the cell, basically, right? Or the water that's inside the cell. Extracellular fluid basically means any fluid that can be found outside your cell, right? Very self-explanatory. Now, the difference is when you look at the extracellular fluid, guys, extracellular fluid, which is the fluid you find outside your cell, you can find it in two different places. Okay, I'm just going to show you this. So Don't care about the numbers. You guys can completely ignore those numbers. That's physiology. We're not going to go into it. So the extracellular fluid, look at it's basically everything depicted in blue. The fluid that is found around my cells or outside my cells. Now remember this little structure right at the center, that was your cardiovascular system, right? So the blood that is found, the fluid or the water that is found inside your bloodstream, that is called plasma. If this is the fluid that's not part of the plasma, but it is still outside my cells, it's called what? Interstitial fluid, or ISF. I never use the word ISF, I just call it interstitial fluid. So one more time, I'm gonna say it. If the fluid is outside my cell, it's called extracellular fluid, or ECF. If that fluid is limited to my blood and my cardiovascular system, it is plasma. And if that extracellular fluid is outside my blood, but around my cell still, it's called the interstitial fluid, as in the fluid found outside the cell, but not part of the plasma. Is this making sense to everybody? I don't go into, so somebody asked about lymphatic system. Lymphatic system is a fluid that's technically interstitial fluid, but it has its own name called lymphatic fluid or lymph. So technically it's still identified as interstitial fluid because it's not part of plasma. Oh, yeah. It's very unfortunate, but I'm assuming it's because there's been they remove lymph nodes. Is that why? Oh, it's just her condition. Okay, I know a lot of people have a lymphedema because they have had some sort of surgery as a result of like cancer. So they to protect the to prevent the cancer from spreading to the rest of the body, they remove the lymph nodes, and that prevents the effective circulation of the fluid. So if that didn't make sense to the rest of you guys, that's fine. I was just answering a question in the chat box. Okay, so let's go ahead and take a look at our phospholipid bilayers, guys. So phospholipid bilayer is the same thing as our plasma membrane. So remember, we said plasma membrane is the boundary around your cell. So that boundary is also called phospholipid bilayer. And I want you guys to just look at the word phospholipid bilayer and tell me, what do you understand from that? So phospho implies what, guys? It contains what? Anybody would understand that one? Let's break it down piece by piece. Phospho does not mean lipid. So phospho means phosphate, right? Lipid means fat, correct? And what does the word bilayer means? Two or double layer, correct? So again, break down the word for yourself. Don't make it complicated, guys. So phospholipid bilayer means it has two layers that is made up of what? Phosphate and lipid, correct? Seems pretty straightforward, right? So if I'm looking at the plasma membrane or the cell membrane that surrounds the cell, that sets the boundary, 75% of that phospholipid bilayer is going to be what? Phospholipid. So that means it contains phosphate heads, or these little circles that are called phosphate heads, which are these ones right here. Okay. And in these little squeaky lines that you see, these are called fatty acid tails. Fatty acid tail. And remember, fatty acid basically means these are fats, right? Chains of fats. So, oh, sorry guys, go back. So if you're looking at this, and I'm gonna just kind of show you a cell right here, okay? Here's my cell. The red line that I'm picking for you guys right here is my plasma membrane or my phospholipid bilayer, which is what we're talking about here. And the other thing I want to ask you guys, if I say, where can you find water in this image? Here, inside, outside, or both? Both, right? Because we just established that you have intracellular fluid and extracellular fluid, right? So you're gonna have water here, right? H2O here, if I can type, right? And then you also have H2O here. Okay, so water on either side of the membrane. So the component that is coming into contact with water should be happy with water, right? The component that is hidden in the middle has, if the image is different, that's okay. Is that just this image, guys? I don't know. It says the image in the PDF is different. Okay, I'll take a look in just a second. So if you're looking at this image, okay, somebody's saying the images are different, somebody says the same. So I'll just stop in a minute and I'll just check it. So when you're looking at this picture and you're looking at the fact that there's water on both sides, right? You have phosphates and you have lipids inside the plasma membrane. The part of the plasma membrane that is coming into contact with water is the phosphate heads. They like water. They like to interact with water because they are in direct contact with water at all times. Think about fat. Does fat likes water? Yes or no? Fat doesn't like water, right? So it's gonna go and hide in the middle. So it's not gonna come into contact with the water that's outside and the water that is inside, correct? So let's take a look, guys. It says phosphate heads are called hydrophilic. Hydrophilic. The word hydro means water. The word philic means loving. So phosphate heads, I'm going to say this slowly. Phosphate heads that like to interact with water have a characteristics that called hydrophilic. On the other hand, the fatty acid tails, the little stringy lines that we have here, that don't like to interact with water, that hate water, they're gonna go hide. They're scared of water, right? They're called what? Hydrophobic. When somebody has phobia, what are they? If you have phobia, like arachnophobia, it means fear, right? You're scared of something. So hydrophobic is basically means you're either fearing water, you want to avoid it, you hate water, whatever you want to call it. You just don't want to come into contact with water. So in this bilayer that I'm depicting in this image, you have your hydrophilic heads right here and right here, which are phosphate heads. And then the fatty acid tails that are hating water, fearing water, scared of water, whatever you want to call them. They are hidden in the middle. And again, here's one layer. Here's the second layer. And that's where the word bilayer comes from. Is this making sense so far? Any questions? Awesome. So the rest of the membrane also have fat. So you got to remember, guys, remember cholesterol, we said fats are really good. It's important, we need to have it. 20% of your membrane is cholesterol. So we have to eat cholesterol. You have to consume that healthy fat to be able to maintain your phospholipid bilayer. And the other 5% is glycolipids, basically glycogen and fat, lipids and sugar put together, and it's a relatively small percentage. But again, if I say, what is majority of your phospholipid bilayer made up of? You would say phosphate heads and fatty acid tail, phosphate heads and fatty acid tails. That's what most of your membrane is made up of. Now, the next thing that we want to talk about is what we have as membrane protein, guys. So remember what I said about the characteristics of your membrane. I said you can allow things to pass through this membrane and some things that just can't get through the membrane. So these plasma membrane are basically, these plasma proteins are basically a way for your cell to communicate with other cells and also to allow things to get into the cell or get out of the cell. So what are these categories of these membrane proteins? So look at these two pictures, guys. This is really easy and again, straightforward. Don't make it complicated. You have proteins that are completely embedded through this phospholipid bilayer. Basically what you see as this gigantic blob that extends from the top all the way to the bottom. It just goes through the membrane, okay? No, these are proteins, they're not fat, remember? So fats are not protein, proteins are not fat. So these are integral proteins that are passing through the double layer of your phospholipid. These are literally, look at the word, guys, integrated or built into your plasma membrane. So they're called what? Integral protein. There are proteins that you see, this little blob right here or the blob that is hanging on the outside. They're just sitting either on the outside surface or the inside. So they are in your periphery on the side, right? They're not part of it. They're on the side of the membrane. So these are called what? Peripheral proteins. So peripheral proteins are either on top or on the bottom, inside or outside. Now, why do I need these integral proteins? Again, integral proteins are ways for me to get things into my cell or out of the cells. So they're kind of like channels. There's these openings or gateways that allow things to get in or out of my cell. So yes, these are channels. Peripheral proteins are usually say, kind of like, hey, how are you doing, from one cell to another cell. They're really not as involved in getting things into the or out of the cell. They're just kind of like a handshake between one cell to another. Sometimes they act as enzyme in what we call secondary messenger system, which you don't need to know. But the main job, if I say, what is the role of integral protein? You say transport proteins. They get things in and out. If I ask you what's the main function of peripheral proteins, your answers would be cell-to-cell connection, communication between your cells. Okay? So the other part that I want to make sure this is clear is that many cells that we have in our bodies are connected to their neighboring cells. So kind of like think about when you live in an apartment or you live in a condo, you share walls with each other, right? One house is sharing another wall with another house, right? Now, in terms of your cell, if you think about every housing as one single cell, each of these cells can be connected together via different junctions. And I'm gonna laugh at me, but that's okay. So one of these junctions is called tight junction. Tight junction basically means I have no space from one membrane to another. Literally, let's say you are sharing the wall together with nothing in between, okay? So basically, it's not like somebody can walk between your house and your neighbor's house because there's no space. They are tied together, they're held together really tightly. They kind of almost merge together and they don't allow things to get in and out between that membrane. A really good example of tight junction is your stomach. So think about your stomach. What is the environment of your stomach, guys? What type of environment it is? It is acidic, right? Now, your stomach can handle that acidity. But can the tissue around your stomach suffer that acidity or deal with that acidity? The answer is no, correct. So how do I make sure that the acidity of the stomach, that acid stays in the stomach and cannot leak out of my stomach? I use what? I use my tight junctions, correct. Not all the junctions, just the tight junction. Just the tight junction, which basically doesn't allow anything to pass through. Now, another scenario that I have is what we call desmosomes. Another type of junction that we have is called desmosomes. And desmosomes is really cool. So imagine your heart, guys. Cardiac muscle is basically your heart. Your heart is beating basically from the first 5 weeks of the embryo development all the way to the moment that you're pronounced dead, basically, right? So it beats every minute of every day. Well, we hope that it beats, unless you have a heart attack too. So basically, these heart muscles that are right next to each other, they're under tremendous pressure to always contract, relax, contract, relax, contract, relax, right? Like anything else, these heart muscles have wear and tear on them, right? As you use them more, they have more wear and tear on them. There are also, the other thing is that, you know, like if you look at, let's say you're wearing your pants, right? And if you put your phone in the same pocket over and over and over again, what happens to your pants? I know it seems like not connected, but I want you guys to process this. So if you're putting this, you either it stretches, you get it tear, right? It gets worn, right? You basically, a lot of times I see you have the design of your phone in your pocket and then eventually it's gonna get worn out, right? So heart muscle is the same way. If you continuously use it over and over and over and over and over again, what's gonna happen to it is that's eventually gonna cause a rip in your heart muscle, which is not something you can replace, right? So what is the job of your desmosomes? So the desmosomes are gonna connect the heart muscles together, and it doesn't allow one point of pressure in your heart. So instead of the corners of your phone leaving those marks in your basically pocket and eventually cause damage, you're gonna take that phone and spread it evenly between the heart muscle cells or between all of the parts of your heart. So instead of having the corners showing and eventually wearing off, you have the whole structure wearing off equally. It's not without the pressure, it's even distribution of force or pressure. There's a difference. So you don't have any corners basically. It's like a gigantic sheet that gets the same amount of pressure throughout. Okay, so you don't have wear and tear because of significant use on a specific part of your heart. Does that make sense, guys? Yes, no? Okay. So cardiac muscles in terms of desmosome is spreading the forces or pressures, and it has it right here so you guys can read it. It says, it helps from the internal tension reducing network fiber. So basically you distribute the tension, so there is no point of tension that can be damaged as a result. D means without, correct. Not in this case though. Desmosomes is just a word. Okay, the third type of junctions that we have, the third type of point of connection we have is what we call a gap junction. So if you're thinking about your house and your neighbor's house, okay, think about you have between the shared wall that you guys have, you have a window that you can connect to your neighbor and pass sugar from one to another, right? So gap junction is a way for your cell to communicate between one cell and its neighboring cell. So cardiac muscle also has that gap junction. So you kind of see that there's this opening right here that extends from one cell, which is right here, to the neighboring cell. And literally things can pass this way or they can pass this way. So it doesn't matter which way it goes as far as that movement of ions or components from one cell to the neighboring cell. Yeah, it's kind of like a tunnel that basically connects things together. So one thing, a couple of things that you guys need for in terms of these junctions. First of all, kind of understand the explanation. So tight junction is basically cells are held together tightly. Desmosomes, the main function is to basically reduce tension on a specific point. And gap junction, the main purpose would be communication. And then for the examples of this, best example for tight junction would be your stomach. And then your heart would be both for the desmosomes and the gap junction. Correct. Your heart has both of the junctions, correct. So stomach, intestines, urinary system, without me going into too much detail and make it too complicated, they have what we call tight junction with exceptions to the rule. Gap junctions are typically found for the purpose of spreading electrical impulses, not for passing things from one another to another. It reduces tension. So the question is, what does desmosome reduce? It reduces tension. So it's tension reducing network of fibers. So it evenly distributes the tension rather than having points of tension throughout the tissue that can be damaged. Does this make sense so far, guys? What time is it? I have about 15 minutes left. So I'm going to cover a few more slides and then we'll close up for today. So we're good, guys, with the junctions. So know the definition and know the examples that I provided, because I can say which kind of junction can be found in your heart, right? And you should know both desmosomes and gap junction. What is the importance of tight junction? It's to make sure that nothing basically passed between the cells, right? It basically holds things tightly together. Okay, so take a deep breath and take a sip of water. Delicious cold water. Okay. So when we looked at the membrane, guys, one of the things I said is if this is my cell, okay, things can get in or get out of my cell, right? But can everything get in and out? Yes or no? No, right? So we said the membrane is kind of like a border, right? It allows things to get in and out, but it controls what comes in and out. So it is, the keyword here is what? Selectively permeable, as in you can select certain molecule to pass through, but the other ones you may have some kind of question mark for them, so you have to wait. So pay attention to this, guys. I'm going to kind of deviate from the PowerPoint a little bit to kind of help you understand the general idea, and then we'll come back to actual terminology. So when you're thinking about molecules or components or atoms or ions or whatever get in and out of the cell, the first question you need to ask yourself is this process require energy? So do I need to provide it some sort of energy, including the most common type of energy, which is your ATP? If the answer is yes, it's referred to as an active process, as in I need to actively put energy into the process. However, if the process of moving molecule either into the cell or out of the cell, it just happens without me putting any effort into it, then that's referred to as a passive process. Are you with me so far? First question you want to ask yourself, energy needed? No, it's a passive process. Energy needed? Yes, that's an active process. So the word that keeps popping up when we're talking about passive process, the process that doesn't require energy, is the word diffusion. So can you guys tell me what diffusion is in your sense. So when you say a scent is being diffused, or a dye is diffused in water, or sugar is diffusing in my coffee, what does that word diffusion imply, guys? So something being spread out, things being distributed, things going from high to low. Dissolving may not apply to every case. Mixing is a good one, yeah. So mixing in what sense, guys? So do I just mix it and then just keep mixing it and mixing it and mixing it? Mixing it until what point? It is equal distribution. Correct, you guys got it. So it's spread all over, equal distribution. So let's go back to this whole concept again. So when I use the word, I'm diffusing something, okay? Anytime you hear this word, it means at one point, at the beginning, I had a huge amount of molecule in one place, and then very low or nothing at the other end. And diffusion, what it does, it allows the molecule to go from what? From high concentration to low concentration. From where I had a lot to a place that I have very little or nothing at all. And that process continues. Look at my hand. I hope you see it. Look at my hand. This process of distribution from high to low continues until when? Until I reach equal amounts or equilibrium, correct? So the concept of diffusion, guys, first thing and the most important thing you need to remember is it goes from high to low. The movement is always high to low. And the way I tell my students to think about, yes, kind of like the balance beam. So like kind of high and low, and then you're eventually gonna reach the same level. The way I tell my students to think about this as a passive process is a stone rolling down a mountain. Do you need to put effort in pushing that stone down the mountain? The answer is no, right? Because you're moving from high to low. So whatever energy that was stored in the stone just gets used and the stone just rolls down the hill, right? When it gets down the hill, done, right? There's no more movement. So same concept applies here. Diffusion is from high to low until you reach equal amounts on either ends. Now, is everybody on the same page so far? Make sense? What the word diffusion implies? Okay. So in this scenario, when I'm talking about diffusion, we're talking about, again, here's my cell, things getting in, right? Or things getting out. It doesn't matter which direction. A lot of people, they say diffusion is just from outside to inside. They use what word inside and outside, or outside to inside. No. Diffusion is anywhere you have high and low, and you're moving from high to low. So pay attention to this. This is really important, guys. If I have a scenario where these molecules that I have that are moving from high to low, they just do their job and they say, I don't need any help from anything within the cell to move from high to low. We're not talking about energy, guys. It's still from high to low, which means no energy. But I say, I'm just gonna zip in and out anytime I want because I'm small and I'm cute and I can get in and out anytime I want, okay? That is called simple diffusion, okay? I don't need any help. I can go from high to low until I reach equilibrium. That's simple diffusion. And I'm gonna take these out so you guys don't need to know that. What if, here's the keyword, guys. Again, common misconception. What if I still move from high to low? Okay, so the word still would be diffusion, but I need something to help the process along because I'm too big, I can't move, or I have too much charge on me and I can't move. So I need something to facilitate the process. When you have a facilitator, what are they doing? Helping along, right? Helping the process along. So if I need to use the protein, remember the integral protein we talked about here? Remember this gigantic protein? What if I need to use this protein to get things in or get things out? If I'm using those protein, guys, then I'm needing what? A facilitator. So I'm still moving from high to low with help of the integral protein. So I call that facilitated diffusion. Do we need ATP, guys? No, because what are we talking about? Diffusion is what, guys? What process is diffusion? It's a passive process. And what is passive process means? No energy. So again, this is really important, guys. Anytime you hear the word diffusion, do not think about any source of energy. You don't need energy to carry diffusion. It's always high to low, which means it's passive. And here is the first thing, requires no energy, right? That makes sense? I don't know who asked the question, so hopefully it made sense. Okay, awesome. Now, the third type that we have is called osmosis. So osmosis is simply diffusion of water. So I cannot, highlight this for yourself, I cannot use the word osmosis for anything other than diffusion of water, which means when my water moves from high to low, I'm gonna use the word osmosis. If it's sodium, potassium, calcium, chloride, anything, oxygen, carbon dioxide, if it's anything other than the water, then it's either simple or facilitated diffusion. If it's water diffusion, it's called osmosis. Make sense, guys? So look, it's a lot of work. I know you guys are like, oh my God, this is too much. We're keeping it simple, guys. Don't care about movement or collision of the molecules. The key word here is what? Molecules of the high area concentration is scattering to the area of what? Lower concentration. Yes, water is only, osmosis only for water diffusion. And I'll have a slide for this in just a second. So diffusion is movement of molecule, what we call down concentration gradient. Remember the stone moving down the mountain, which is basically means high to low. It does not require any energy. Another way of saying high to low is moving with concentration gradient. Again, high to low. Concentration gradient means high to, sorry, I really need to connect my thing. High to low. Now, what can affect my diffusion rate? How fast can these molecules diffuse? Kind of think about it. If you have a kind of a relatively larger molecule, it's gonna move slower, right? That kind of makes sense. Higher temperature increases diffusion rate. Can anybody give me an example of this? Higher temperature increases diffusion rate. Okay. You said coffee, but what coffee? What about coffee? Okay, something is easier to dissolve. Okay. Okay, so I'm gonna just kind of try to read your mind. So higher temperature increases diffusion rate. When you add sugar to a hot coffee versus a cold coffee, which one dissolves faster, right? Which one spreads the sugar evenly in your solution? The hot coffee, right? Or hot tea or whatever. So the hotter the solution, the higher the temperature, the faster that diffusion rate takes place. The colder it is, the slower the diffusion rate is. Thank you. Now here's another, again, example of diffusion. You have high concentration of that dye, and then eventually it evenly distributes itself. This is a really good concept. I just want to kind of go over it. If the plasma membrane is damaged, so it can be as a result of some sort of trauma or burns, then you don't have that kind of concentration gradient that we're mentioning, right? There is no diffusion, there is no facilitated diffusion, there's no osmosis, because everything can easily get in and out of your cell. There is no plasma membrane. So patients that have severe burns, so the tissues are damaged, then basically, again, things can leak in and out of your damaged cell, and those cells are basically dead. You can't really do anything with them. Okay, so in the response, what is the components? I just need you guys to focus on the examples here. What are the examples of molecules that move through simple diffusion? These are oxygen, carbon dioxide, and fat-soluble vitamins. The characteristic you need to remember is they are fat-soluble and they are small in size. So remember the examples, guys. Examples are super important. Here is just kind of a picture. You can see the oxygen, carbon dioxide, water, ethanol, things like this can easily pass through the membrane. Benzene can easily pass through, hence it's a very bad carcinogen, can cause significant damage to the cell. But things like glucose, chloride, calcium, sodium, amino acid cannot pass through the double membrane. They just bounce off. Facilitated diffusion, again, I don't really need you guys to know any of these details. The only thing I want you guys to know is the definition that is listed up here. Facilitated diffusion is when the molecules, again, go from high to low using your integral protein, with the help of your integral protein. So kind of simplifying this. You go into a lot more detail when you do physiology for this. And then lastly, osmosis. Osmosis is only what, guys? Diffusion of water, correct. So movement of molecules such as water across a selectively permeable membrane. Water diffuses through the plasma membrane. And one last word before we close up the lecture for today is water can move or diffuse via osmosis. Sorry, guys. Using these specific water channels, which is shown in purple here, called aquaporins. Can anybody break down the word for me? Aqua means water, and what is the word pouring implies to you? What does that remind you of? The second part of the word, pores, right? Holes, right? Openings, right? So a small pore. So aquaporin literally means water holes or water opening or water pores that allows the water to get in and out. So remember, aquaporin is also, again, another key word in terms of you understanding the process of osmosis. Okay. So sorry, we have like 2 minutes left, so I'm good. So we're gonna stop here, guys. Make sure you guys work on your Canvas post one if you haven't done so. Let me stop my thing, actually. Stop my recording. If you guys